Have you ever really thought about what it takes to power those massive container ships crisscrossing the globe? We're talking about colossal engines. Some of them are as tall as a four-story building. But what holds these absolute titans together? Well, today we're going to get into the very skeleton of these machines, the engine frame.
You know, the best way to think about an engine frame is like the steel skeleton of a skyscraper, or even the spine in your own body. Its whole job is to provide incredible strength and maintain perfect alignment for all the moving parts inside. It's really the unsung hero, silently withstanding unbelievable forces deep in the belly of a ship. Okay, so here's our game plan. First, we'll break down what the frame actually does. Then we'll check out how different designs are built for different jobs. After that, we'll see what happens when things go wrong, dive into the super meticulous repair process, and then we'll wrap it all up with the key engineering takeaway.
All right, let's start at the very beginning. What exactly is this backbone? And what is its absolutely critical role inside that massive engine?
So at its core, the frame is the rigid foundation. I want you to picture this. Inside the engine, you've got thousands of controlled explosions happening every single minute. The frame's job is to contain all of that immense force, absorb the constant violent vibrations, and make sure every critical component, from the crankshaft to the pistons, stays aligned down to the millimeter. Seriously, without that rigid structure, the engine would literally just tear itself apart.
But of course, one size doesn't fit all. Just like the engines themselves, the frames come in all sorts of different designs, and each one is brilliantly engineered for a very specific job.
For medium-speed engines, two of the most common designs you'll see are the V and inline configurations. The inline is pretty much what it sounds like, a classic straight block. The V, on the other hand, angles the cylinders, and that is such a clever design because it often saves a ton of crucial space in an already crowded engine room. It's a perfect example of tailoring architecture to the ship's needs.
Now, a more modern approach, especially for those smaller to medium-sized engines, is the monoblock design. And yep, the name pretty much says it all. It's cast as one single solid block of metal.
And the advantages of making it in one single piece? They're huge. It means less complex machining, which saves a whole lot of time and money in manufacturing. It's also incredibly compact, a major plus when space is tight, and it's a lot lighter. This is just a fantastic example of efficiency driving the entire design process.
Okay, now let's go to the complete opposite end of the spectrum, the truly massive, slow-speed engines that power the world's biggest ships. For these giants, engineers use what's called the A-frame structure, and, well, you can see exactly how it got its name.
Here, form perfectly follows function. That wide base and the angled structure of the A shape give it unbelievable stability, and that's absolutely essential for handling the immense torque these slow-turning, high-power engines generate. It also happens to be the perfect housing for the crosshead guides, which are a key component in these big two-stroke designs. This is just pure, heavy-duty engineering at its finest.
You know, these frames are designed to be unbelievably strong. They're built to last for decades under constant, incredible stress. But they are not invincible.
So what actually happens when the backbone of the entire engine starts to fail? The consequences can be catastrophic, which is why identifying the problem early is everything.
A lot of the time, a failure begins as a tiny, almost invisible structural crack. They usually pop up in high-stress areas, like along vertical welds or on the horizontal support ribs. And you know what the most common culprit is? It's often an inadequate quality check during manufacturing. A tiny flaw, subjected to years and years of immense pressure, can grow into a massive problem.
So you've found a crack in the frame of a multi-million-dollar engine. You can't just, slap some weld on it and call it a day. The repair process is a masterpiece of precision engineering all on its own.
The repair protocol is this high-stakes three-phase operation. First, you have the meticulous preparation of the damaged area. Second, you have to protect the rest of the engine from the intense repair work. And third, you have to control heat distortion to maintain that perfect alignment. Every single one of these steps has to be done flawlessly.
So the first step is all about creating the perfect foundation for that repair. You just can't weld over a crack. The entire damaged area has to be completely ground out, right down to the bare, clean metal. If this prep work isn't absolutely perfect, the whole repair is just doomed to fail from the start.
Next up is protection.
Welding creates intense heat and sends sparks flying absolutely everywhere. You cannot let that damage the precision machine surfaces of nearby parts like the crankshaft. So every sensitive component gets meticulously wrapped in heat-resistant material. It's almost like performing surgery. You have to carefully protect all the surrounding organs.
And finally, we get to the biggest challenge of all, controlling heat distortion. When you apply that much heat to metal, it wants to warp and bend out of shape. To stop that from happening, engineers use these special jigs. They're basically custom-built clamps that hold the frame in perfect alignment during the entire welding process. This makes sure that when the metal cools, it settles back into its exact original dimensions. It's a truly ingenious solution to a massive engineering problem. So, after that pretty deep dive into design, failure, and repair, let's kind of zoom out and lock in the key engineering takeaways from all of this. What we're really seeing here is a story of purpose-built design. The monoblock gives us efficiency through its lightweight and compact form. The A-frame delivers that raw, uncompromising strength needed for the biggest jobs. And the clever use of special jigs during a repair shows how engineers solve these really complex problems to maintain structural integrity. Each feature is a direct answer to a very specific challenge.
At the end of the day, the engine frame really is the unsung hero. It doesn't get the glory of the pistons or the crankshaft, but without its silent, rigid strength, the engines that power global trade just couldn't exist. Simple as that.
And that kind of leaves us with a final thought, doesn't it? The engine frame is a perfect example of this incredible, invisible engineering that we all rely on every single day. So what else is out there, quietly and perfectly doing its job to power our world, completely hidden from view?